Welcome to the 27th lecture of the MOOC on parallel algorithms. In the previous few lectures, we have seen some algorithms that work on interconnection networks, and we shall see some more today. When we discuss interconnection networks, two of the parameters that are of relevance are the diameter of the network and the bisection width of the network. What I mean by the diameter of a network is the maximum distance between any two nodes in the network. For example, when we consider a linear array of size n, the maximum distance between any two nodes in the network is the distance between the first node and the last node, which is n minus 1. So, the diameter of a linear array of size n is n minus 1. Instead, when you consider a two-dimensional mesh, that is n by n, when you consider a two-dimensional mesh of size n by n, the maximum distance between any two nodes will be obtained by going from the top left to the bottom right, for example. That is, start at one corner and go to the diametrically opposite corner. So, the distance traversed would be n minus 1 to come here and then n minus 1 to go here. So, the diameter is n minus 2. This is of course one way of going from the top left corner to the bottom right corner. There are various other paths. As it happens in this case, every single of these paths will have the same length 2n minus 2. Another parameter that we shall often be talking about is the bisection width. The bisection width of a network is the minimum number of edges that must be removed to bisect the network. By bisection, we mean we want to partition the network into two halves so that each half will be approximately of the same size. For example, when we are given a linear array of size 7, let us say, there are 7 nodes here and there are 6 edges. If you remove this edge, the network is partitioned into approximately 2 equal halves. In this side now we have 3 vertices and on this side we have 4 vertices. So, this is as even as you can get in a network of odd size. So, in this case we say that the bisection width is 1. When you take an n by n mesh, a division of the network like this, when n is even, will ensure that the network is partitioned into 2 equal halves. If the network is of odd size, then you can find a partition of this sort, which will again divide the network into two equal halves, approximately equal halves. So, you can work out the details. I am leaving the details for you to work out. So, in either case we find that the bisection width is theta of n. So, in the case of a linear array, the bisection width is 1, the bisection width is very low. In the case of an n by n mesh, the bisection width is not very low, it is not a constant, it is theta of n. Now, what are the relevances of diameter and bisection width? These are useful in proving lower bounds to many problems. For example, let us consider sorting. In the case of a linear array, where we want to sort the elements from the left to the right, let us say we keep the largest element in the first node. The largest element, let us say L, is kept in the first node. Now, when the sorting is over, the largest element has to appear at the right end. For this to happen, the element has to travel through a distance of n minus 1, which happens to be the diameter of the network. So, here we are keeping the largest element a diameter away, so that it will have to travel a distance equal to the diameter to reach the destination. So, this ensures that a lower bound for sorting is the diameter. So, on this case, in this case, sorting requires at least n minus 1 steps. You can make the same argument about a general network. When we are given a general interconnection network, if we know the diameter of the network, then for the problem of sorting, we can take the element that is destined to a particular node and keep this node at its diametrically opposite point. Then this element will have to travel through the diameter to reach its correct position. Therefore, the sorting algorithm is going to take at least that many steps. The time taken would be equal to the diameter. So, the same argument could be replicated for several other problems. When we come to an n by n mesh, the diameter is, as we have seen, 2n minus 2. Therefore, a lower bound is 2n minus 2. This is of course the argument we had seen earlier, and then we went on to improve this lower bound. So, in this fashion, diameter can be used to prove several lower bound results. Then what is the use of bisection width? Let us consider a network of diameter d, or rather bisection width w. Which means there are w edges, the removal of which will disconnect the network into two equal halves. Removal of these edges will disconnect the graph into two equal halves. Let us consider the problem of sorting. Looking at the network, we can decide what should be the final sorted order, that is, where should the smallest element appear, where should the second smallest element appear, and so on. Now, we are given an input, and the goal is to rearrange the elements, permute the elements so that they reach the required positions. Now, if we ensure that all the elements that should go to the right side are placed in the left side, and all the elements that should go to the left side are placed on the right side, then every single element will have to cross the bisection. So, if the network has a size of n, we have n by 2 elements on either side, give or take 1. These elements have to cross over to the other side. Similarly, there are n by 2 elements on the other side that have to cross over to this side. So, we have a total traffic of n that should be going through these w edges. But then each of these edges can move only one element per step. We assume that an edge moves one element per step. This implies that in one step W elements can move across the bisection. But then we have a total traffic of n to be transported. So by the time the sorting is over, n elements would have moved across the bisection. In each step, no more than W elements would have moved. Therefore, we would have spent at least n by W steps. So this establishes a lower bound of n by W for sorting. So likewise, we can find the lower bound for many other problems. We estimate the total traffic that the problem will have to solve, and we will arrange the inputs in such a way that the traffic will be maximized. Then the maximum traffic that is required to solve the problem divided by the bisection width will be the worst case lower bound for the running time of an algorithm for the problem on the given network. So in particular, when you want to sort on a root n by root n mesh, as we have seen just now, the bisection width is theta of root n. The net traffic required is n. Therefore, the lower bound is omega of n by root n, which is omega of root. That is, you cannot expect to sort faster than root n. Of course, we have already seen a precise lower bound for this purpose. But in particular, if we are looking at a higher dimensional mesh, we can use this method to evolve a lower bound. But what is a higher dimensional mesh? First, let us consider a three-dimensional mesh. A three-dimensional mesh is a straightforward generalization of a two-dimensional mesh. In a three-dimensional mesh, we have three dimensions. A node has two neighbors along one dimension, and it has two neighbors along a second dimension, and then it has two more neighbors along a third dimension. So a node could have two neighbors along the blue dimension, two neighbors along the red dimension, and two neighbors along the green dimension. So the maximum vertex degree is 6. But of course, as we know from the two-dimensional case, the corner nodes will have smaller vertex degrees. A corner node in this case can have a vertex degree of 3. So the vertex degrees will range from 3 to 6. So a three-dimensional mesh will look like this. You have multiple two-dimensional meshes. and we have connections between the corresponding nodes. That forms a three-dimensional mesh. So, in this case there are 3 nodes along this dimension, 4 nodes along this dimension, and there are 2 nodes along this dimension. So, if you call this the x dimension, this the y dimension, and this the z dimension, then we can say this is a 2 by 3 by 4 mesh. It has a total of 24 processors. And the maximum vertex degree is 6 and the minimum vertex degree is 3. Such a mesh is called a three-dimensional mesh. Then of course we can go on from a three-dimensional mesh to a four-dimensional mesh. You take points in 4 dimensions and connect them up. In general, you can talk about a k-dimensional mesh for any number k. Now let us consider a three-dimensional mesh which is n power 1 by 3 by n power 1 by 3 by n power 1 by 3. This has a total of n nodes, and these nodes are arranged in the form of an n power 1 by 3 by n power 1 by 3 by n power 1 by 3 mesh. Each node has at most 6 neighbors. What would be the diameter of this network? The maximum distance between any two nodes. Think of this network as a cube where each side is n power 1 by 3. So, if you start at a node and go to the diametrically opposite node, then you can traverse any one of the possible paths. This is one way of going from a node to its diametrically opposite node. So, the distance traversed here is 3 into n power 1 by 3 minus 3. So, this is the diameter of this mesh. Now, what would be a bisection width? I will leave a rigorous proof to you, but to find the bisection width, what you can do is to cut the mesh along this direction using a plane of this sort with n power 1 by 3 by 2 elements on this side and n power 1 by 3 by 2 elements on this side for each x line. An x line is a line of processes that are parallel to the x axis. So, let us say we are cutting every x line into 2 equal halves. Then the number of processes on the left side and the number of processes on the right side will be approximately equal. If n power 1 by 3 happens to be an odd number, then you will have to introduce a kink. A planar cut will not be enough, but still you can devise a cut which ensures that the number of vertices on either side is approximately the same and the number of edges disconnected is of the same order as the number of edges on a plane. So, we are now cutting perpendicular to the x axis using a yz plane. So, the number of edges disconnected will be the number of edges that are on one plane. So, when you consider a plane of this sort, the number of edges here would be theta of n power 2 by 3. So, the bisection width of the network is going to be theta of n power 2 by 3. So, using this, once again we get a lower bound for sorting is the total traffic divided by the bisection width, which is omega of n power 1 by 3. So, you cannot expect to sort n elements faster than n power 1 by 3 asymptotically on this model. Now, let us an algorithm that actually does this, that is, it runs in order of n power 1 by 3 time. So, that is what we are going to see next. In order of n power 1 by 3 time. On an n power 1 by 3 by n power 1 by 3 by n power 1 by 3 3-dimensional mesh. As I describe the algorithm, I will also prove its correctness. For proving the correctness, I will resort to the 0-1 principle, which asserts that if an algorithm works correctly on all binary sequences, it should work correctly on all sequences drawn from a linearly ordered set. So, we assume that we are sorting a binary sequence. If the algorithm works correctly on the binary sequence, it should work correctly on any sequence drawn from a linearly ordered set. So, we are given a mesh. Let me represent the mesh using a cube to indicate the 3 dimensions. Let us say the vertical dimension is the x dimension, the horizontal dimension is the y dimension, and the dimension into the board is the z dimension. So, let us say we want to sort the elements so that the smallest n power 2 by 3 elements will be in the first xy plane. So, if the planes are numbered from top to bottom, then the first xy plane happens to be, or if the planes are numbered from front to back, then the first xy plane happens to be this. So, we assume that the smallest elements are going to be, the smallest n power 2 by 3 elements will be on this plane. And then in addition, we will assume that the smallest n power 1 by 3 of these will be in the first x line. Which is this one. The first x line, let us say, is this one. So, the first xy plane is made up of several x lines. An x line is a line of processes that are parallel to the x axis. So, the one that is marked now is the first x line, then we have the second x line, third x line, and so on. These x lines will form the first xy plane. So, in the first xy plane, we want the elements to be sorted in x major order. In general, we want the elements in the mesh must be sorted in the z, y, x order. What it means is that x is the first major, y is the second major, and z is the third major. In other words, when we look at the elements in sorted order, the x dimension will move first. That is, to find the next element, you should go down the x dimension to the next element. Once the x dimension is exhausted, you should move along the y dimension to find the next. And then once the y dimension is also exhausted, that is, once the xy plane is over, then you should move in the z dimension and go to the next xy plane. So, this is the order in which we want the elements to be sorted. Or in other words, what we want to say is that if the ij kth element is greater than or equal to the I prime j prime k primeth element, then k prime j prime I prime lexicographically precedes kji. That is a formal statement. We want the elements to be finally arranged in such a way that if the element that appears at position I, j, k is greater than or equal to the element that appears at I prime, j prime, k prime, then the pair, the order triplet k prime, j prime, I prime lexicographically precedes k, j, I. So this is the same as the z, y, x order. So when we talk about a two-dimensional plane, using the standard notation, if I write x along the horizontal axis and y along the vertical axis, and if this is how I look at a plane, the xy plane, if I sort in yx order, which is the same as the x major order, x would be moving first. Means to find the next element, for an element you should go along the x dimension. Once the x dimension is over, you should move in the y dimension and then continue so on. So this is the x major order, which according to this figure, if you consider the rows horizontal and columns vertical, this is the same as the row major order. The xy order happens to be the y major order, so this is the same as the column major order. So what we want is that the elements must be sorted in zyx order. So the algorithm proceeds in this fashion. As I describe the algorithm, I will also explain the algorithm using an instance of zeros and ones. If the algorithm works correctly on a binary sequence, it should work correctly on any sequence. So in step 1 of the algorithm, what we do is, we sort each zx plane into the zx order. What it means is that we consider the zx planes, the upward dimension is the x dimension and the into the board dimension is the z dimension. So we consider the zx planes and we sort each zx plane of the mesh in zx order, which means x moves first. So if we are sorting from top to bottom, we will be sorting the elements in this fashion. This is the zx order sorting of a number of bits that appear in this zx plane. That is, the elements are moving first in the x order. The sorted order is moving first in the x order. Once the x dimension is exhausted, we move in the z order. So in another zx plane in which the sorting is proceeding in parallel, we will have the results in this fashion. Etc. So let us say the zx planes are sorted in this fashion. This sorting can be done using the 2D algorithm we saw earlier. Therefore, this step will take order of n power 1 by 3 time. So, in this case we are sorting n power 2 by 3 elements on each zx plane. Each zx plane is essentially an n power 1 by 3 by n power 1 by 3 two-dimensional mesh. So, the algorithm of the last class is exactly applicable. So, the sorting will be over in order of n power 1 by 3 time. Now, look at a zx plane. This zx plane has been sorted. What it means is that in this every x line, the x line is a line which is parallel to the x axis, every x line is now sorted. So, I have used two colors, the light red and the dark red, to indicate 0 and 1. What we find is that there is exactly one x line which is dirty. On each zx plane. I have one sample zx plane here. Remember, x is the vertical dimension and z is the into the board dimension. So, when you consider the x lines, we find that all of them except one are clean. The earlier ones are 0 lines and the later ones are 1 lines. Now, let me consider the x lines here, the z lines here. The z lines are the lines that are parallel to the z axis. A line of processors that are parallel to the z axis will form what we call a z line. So, let us consider the z lines. When we compare two z lines here, we find that they have approximately the same number of ones. There can be a difference of at most 1 in the number of ones between two z lines from the same zx plane. So, what we find is that take two z lines from the same zx plane, they differ by at most 1. In the number of ones. Two zx planes differ by, two z lines from the same zx plane differ by at most 1 in the number of ones. Now, let me consider two yz planes. Consider any two yz planes of the mesh. When you consider two yz planes, we discover that these yz planes are made up of corresponding z lines. Take these two z lines, they belong to the same zx plane. Similarly, you take two z lines here, they belong to the same zx plane. So, these two yz planes are made up of pairs of corresponding z lines, where each pair belong to the same zx plane. Now, from our conclusion in the previous slide, what we know is that between these two pairs, between the elements of each of these pairs, there is a difference of at most 1 in the number of ones. That is, these two z lines differ by at most 1 in the number of ones, so do these two, and so on. So, if you aggregate over the entire yz plane, the two yz planes, we find that they differ by at most n power 1 by 3. These two yz planes differ by at most n power 1 by 3 in the number of ones. That is because every yz plane is made up of z lines. Therefore, if you take two yz planes, for every z line here, take the corresponding z line on the other yz plane. These two z lines will fall on the same zx plane, and therefore they differ by at most 1 in their number of ones. Therefore, if you aggregate over these two yz planes, we find that they differ in at most n power 1 by 3 in the total number of ones, because the total number of z lines is n power 1 by 3. Now, what we do in step 2 is to sort each yz plane in zy order. We sort every yz plane in zy order. Mind you, in this sorting as well as the sorting of the previous step, we assume that the sorting is not done in a snake-like order, but in this order. When we sort a plane here, we assume that every row is sorted in the same direction. But this is not difficult. If you manage to sort them in snake-like fashion, then we can switch the order of every alternate row in order of n power 1 by 3 time. Therefore, the time taken for this first step as well as this step is order of n power 1 by 3. So, we have now sorted every yz plane in zy order. So, when you look at a yz plane, what we find is that it is sorted in this fashion. The yz plane is now sorted in this fashion. Y is the horizontal dimension and z is the into the board dimension. So, every yz plane is sorted in this fashion. When I take another yz plane, we find that the kink in that yz plane, the kink is the point at which zeros transition into 1. So, the kink here happens at this point, the switch from zeros to 1. So, the position at which the kink happens in two yz planes differ by at most n power 1 by 3. So, if I take another yz plane, I find that the kink in that yz plane is happening roughly at the same place. It could be in the adjacent row. So, that is the earliest when I take the earliest yz plane and the latest yz plane in terms of the position of the kink, we find that they differ by at most n power 1 by 3, or in other words, all the kinks are happening within a window of n power 1 by 3 positions. We have a window of n power 1 by 3 positions in which all the kinks happen. What this means is that when you look at the entire network, the dirty y lines in every zy plane, there are only two such aggregating over all the zy planes of the mesh. In other words, there are at most two dirty xy planes. Y lines from all the zy planes aggregated together will form an xy plane. That is, if I take the first y line from here, if I take the first line y line from the next zy plate and so on, if I aggregate all of them, I will get the first xy plane. Now, here I find that this plane has exactly one dirty row, dirty y line. When I go to another yz plane, the dirty y row there could be either the same one or the adjacent one. It cannot be any other. Therefore, there could be at most two dirty xy planes in the entire mesh. This could be one dirty xy plane, or this could be another dirty xy plane. So, there could be at most two dirty xy planes in the entire mesh. So, now all that is left is for us to fix these two xy planes, but the problem is that we do not know which are these xy planes. We know that there are only two xy planes in the worst case, but we do not know which two. Since we do not know which these two dirty xy planes are, what we do is this. In step 3, we sort each xy plane in yx order. That is the x major order. Every xy plane is now sorted in the xy order. We know that there are only two dirty xy planes. Both of these xy planes are now sorted. But then here we do not sort every xy plane the same way. We alternate the sorting order. We sort the odd planes one way, the even planes the other way. Our purpose is to do exactly that what we did in the case of shear sort. Let us say in a two-dimensional case, consider the two-dimensional case. Let us say we have two dirty rows that are sorted in the opposite direction. We saw that if we compare and exchange them position by position, with the smaller element going to the top and the larger element coming to the bottom, we saw that at least one of the rows will become a clean row. In this case, the bottom row has become a clean row, whereas the top row continues to be dirty. But if the number of zeros and the number of ones exactly match, then we will have two clean rows. This we had seen earlier in the previous lecture. So we are going to use essentially the same concept here. The situation here is that we have two dirty xy rows, but we do not know which of them are dirty, which those two are. Therefore, we sort every xy plane in yx order, alternating the sorting order. The odd planes are all sorted in one direction, the even planes are all sorted in the opposite direction. Then the two dirty xy planes will be in a situation that is similar to those of these two rows. They are pitted against each other, and then if we compare and exchange in this fashion, we can ensure that at least one of them will turn a clean xy plane. So we will be left with only one dirty xy plane if we manage to do this. But then the problem is that we do not really know whether they form an odd even pair or an even odd pair. Therefore, to rectify this problem, in step 4 what we do is this. We do two steps of odd even transposition sort on each z line. That is, we are going across the xy planes. So if we look at the two dirty xy planes, it could be that in the first step they are paired off with others. It could be that the dirty xy plane at the back is paired with the plane which is further to the back, and the one in the front is paired with the one which is further to the front. Then the compare exchange will not create any difference. That is, the first step of the OETS that we do will not make any difference. Even if this is the case, in the next step these two will be paired together. When these two are paired together, at least in the second step of the odd even transposition sort that we do here, there will be an exchange. If they happen to be paired in the first step, no worry, one of them will become clean in the first step itself. There could be at most one dirty plane in the next step. So in the next step it will be paired with either to the front or to the back. That will not make any difference, because to the front we have all zeros and to the back we have all ones. So therefore, a compare exchange in the second step will then be a waste, will be unnecessary, it will not make any difference to the mesh. But either way, once we do this, that is, we do 2 steps of odd-even transposition sort on every z line. Once we do this, what we ensure is that there is at most one dirty xy plane. But of course, we do not know the identity of this xy plane, we do not know which of the xy planes is dirty. Therefore, what we do in the next step, in step 5, we sort every xy plane in yx order. This ensures that every xy plane is now clean. And the entire mesh is sorted. So this algorithm works correctly on a binary sequence. So doing a quick recap, the steps of the algorithm are just these. We sort every zx plane in the zx order. This will take order of n power 1 by 3 time by the algorithm that we saw in the previous class. So after sorting every zx plane, in the second step we sort each yz plane in the zy order, which again will take order of n power 1 by 3 time using the same algorithm. And then in step 3, we sort every xy plane, but alternating the order of the odd planes and the even planes. This will again take order of n power 1 by 3 time. We are using exactly the same algorithm once again. Then in step 4, we do 2 steps of odd-even transposition sort along each z line. This will take order of 1 time. There are only 2 steps to perform. And then finally in step 5, we sort every xy plane in yx order. This will ensure that the entire mesh is sorted in zyx order. So this also will take order of n power 1 by 3 time. Therefore, on the whole, this algorithm runs in order of n power 1 by 3 time. Which means n items can be sorted in order of n power 1 by 3 time on a 3-dimensional mesh. Now going further, it can be shown that, even though we will not show it here, for a constant r, n items can be sorted in order of n power 1 by r time on an r-dimensional mesh which is regular. An n power 1 by r sided r-dimensional mesh, n items can be sorted in order of n power 1 by r time, which is a generalization of the result we have seen just now for constant r. Of course, the result will not work when r is not a constant. So that is a result for sorting on multidimensional meshes. Okay, that is it from this lecture. Hope to see you in the next lecture. Thank you.